Today I'm going to present my papers on the wavelet scattering transform for multi-class support vector machines in the audio device classification systems. My name is Dr. Chin. My co-author is Dr. Zhang. Introductions: and audio-based context recognition systems could classify sound from different devices. This is one of the typical examples where we have a lot of device that's used to record the sounds. So what we do in the acoustic scenes classification is that we try to classify the sound according to different scenes, maybe metro stations, urban parks. But for this case, we are trying to classify the sound from different devices. The top performing systems is in the DK's 2020 challenge. It consists of multiple models using the CNN. Okay, CNN is the convolution neural networks. Most of them are using the example CNN, which is quite computational exhaustive. So as a result, multi-layer perceptrons and support vector machines were used as example classifiers. How we extract the features. The wavelet time scattering has shown to perform well beside the Male spectrograms or even the log Male spectrograms that they often use to extract the features. Why we want to choose the wavelet scattering is they are insensitive to translation, rotations, and small deformations. They produce a more accurate classifier in dealing with variations in the acoustic scenes classifications or even in the device classifications. So multiple spectrograms such as the MFCC, short time Fourier transform CQT, are also in use. They even combine them to increase the features used for trainings, but however the training time will increase. ACR for the sound device and multi-class SVM classifier using the wavelet features for automatic classification has not been studied widely, so this is why we decided to have these papers. For data sets, the environments at the set contains data from 10 cities and 9 devices. Okay, 3 real device ABC and 6 simulated device named S1 to S6. As you can see from here, this ABC were recorded from the real device and S1 to S6 is simulated. And you can see that if you look at another columns, the train segments, the total train segment is 13965. The text segment is 2970. So the total of this is basically this additional of these two is 23040, and they are having a total 64 hours. Alright, so that the data set from S4, S5, S6 are not available. So hence it makes the evaluations more difficult as the data set is not seen or being used during the training stage. So the average data augmentations, which is what we call the mix-up methods, is basically used to enhance on the ACR for unknown recording devices used for recording the acoustic scenes. So what we do here is that we do a mix-up to improve the trainings, and the features and label are also mixed. And you can see that the allocations of features for unseen recording device are groups, meaning that they are add together, and average, meaning that for this case they divide by 3, and for these two they divide by 2, and so on. So you can see that this will represent the new data for S4, which is not available, and the label are S4. For example, the labels for recording device after being averaged are given the phone label S4, as I mentioned just now, S5, and this S6. So I just want to briefly go through the multi-class support vector machines using the linear kernel, which is something that we will be using, and this is not a new methods. So SVN is one of the supervised machine learning algorithms used for classifications. It uses techniques that call the kernel tricks to transform the data and then mix on these transformed data to find an optimum boundaries, which is for this case optimum boundaries and between the possible out. So this is something that we always try to have a maximum margins linear classifier so that we'll have a clear separations of the black dot and the white dot for this case. So the proposed methodologies is shown in the flowchart here. So first, the input audio signal will undergo the scattering transform to extract features for sound source, followed by the average data augmentations as I mentioned. Then the main parameters for the wavelet scatterings is the number of wavelet filter banks, duration of time invariance, number of wavelet per octave. So in this case, the first scan filter band were used and has 4 wavelets and 1 wavelet per octave. The invariance scale that we use is 0.75, correspond to slightly more than 22,050 samples for the sampling rate of 44,100 Hz. For the multi-class vector machines, for this case, we were using that. There's many classifications, so you will find that we will use the majority votings, which combine the individual predictions, and then by using the methods multi-class support machine vectors, then we will make the final predictions on whether the sound come from the device A, B, C, S1, S2, S3, S4, S5, S6. So just to give you some rough idea that the feature matrix of the training data set has now 55,848 times 290 features, and for text data set is definitely less than that, is 11,868 times also 290 features. So let's look at the results and discussions. So we try to compare with different kernel functions, as we know that not only the linear kernel functions, that we have other kernel functions as well. We tested this on our laptops, the Intel Core i7, the 2.6 GHz 6 core, and with the graphic card GeForce RTX 2060. So you can see that the kernel functions that we try to compare here is the second, third order polynomial linear that we have chosen, the radial basic function and sigmoid functions. 1 versus 1 as compared to the 1 versus all kind of classifications. So you will find that the linear perform better than the rest, but you also can observe that with higher order polynomial functions and using the Gaussian distribution on inputs, the device-wise classification accuracy does not really improve, and it seems that 1 versus 1 of constructing the MC SVN produce a better classifications accuracy than the 1 versus the all, which you can see from the difference. So with the smaller number of trainings data required for 1 versus 1, the computation effort is more efficient as compared to 1 versus all kind of classifications. So you can see the confusion chart here. You can see the blue color indicate that the classifications, the accuracies. This is something that we have produced using the SVA kernel functions via the linear kernel functions. As we compare to other type of classifiers, there's different types, but we try to compare the one that we mentions, linear kernel functions, and also with decision trees, multi-class naive Bayes classifier, and the common one is the KNN. So you can see that methods that we propose is 69.7, which is around the 69.8 as mentioned, and it still remain as the highest one or the most accurate classification that we have achieved. And you can see that compare using the decision trees, the classification accuracies, naive Bayes classification and the KN are shown here in the tables, but they don't really perform well as compared to the multi-class SVN with the linear kernel functions. We have also tried to determine the final misclassification rates via the tenfold cross validations, and you can see that it's still very small, like 0.56%. As compared to the rest is 21, 47, and 18. So this is the tenfold misclassification rates that you can see through the tenfolds. And the proposed multi-class SVN with linear kernel function has the lowest misclassification rate of 0.56%. So if you convert to percent, it's actually 0.56. If you really compare with the multi-class naive Bayes classifier has not performed well, is due to the variable in the dataset are dependent on one another, so it's very difficult to achieve a very low misclassification rates. So if you compare with other, probably with the CNN, which the baseline they're using a CNN with these structures, alright, so there has a couple of layers, okay, which is a very common one that is flattened, and then there's dense net and there's output that using the softmax activations functions that produce the final classification results. So there's a dropout of 30% that you can see that will help to improve the generalizations. So most method actually uses CNN, and even some of these pre-trained network such as the ResNet and the DenseNet to achieve a higher classification accuracies. The top winners for the DK's 2020 challenge, they use the snapshot example deep learning neural networks. Okay, they achieved 76.5% as compared to us 69.8. We are having a shortfall of 6.8%, but it still remains the top quartile of the total 179 entries from the 47 team globally. And if you compare with their CNM 54.1, and we are actually higher than their baseline, so meaning that this method is feasible, and in fact it has a shorter computation time, which is not indicated here, but we know that if you use CAN, the time will longer. So as a conclusion, wavelet scattering feature extractions for the multi-class support vectors with 1 versus 1 approach using the linear kernel functions was used for the classifications. The average based data augmentations on the scalar coefficients improved the classification accuracy of unseen device, and also we achieved the accuracy of 69.8% as compared to 76.5% using a snapshot example. However, it still remains higher than the original baseline system using the CM, which is equal to 54.1%. So with that, thank you very much.